if we look at the second order conditions for stable equilibrium for a homogeneous state, so we assume the homogeneous state, this satisfies the Gibbs criterion for stable equilibrium, that is it has a minimum energy, right? Then we showed, we sort of stated without proof that this is a point of convexity, or strict convexity for the surface. Main condition that is relevant to us is that this implies that the second order or Hessian matrix is positive semi-definite. That actually means that these quantities, the principal minor, because first is ES, the second principal minor is a determinant itself. Those are non-negative. So to overcome the difficulty posed by this possibly becoming zero, I will use the earlier invertibility conditions that we established for the existence of the Legendre transforms such as A, H and G, and conclude that this cannot be zero, and this we have to wait before I remove that. Further, we can also show that EBB has to be greater than zero. So now let us look at what these conditions mean for the, so if you look at this, D equal to TES minus DET, and D is DE by DS at P, and P is minus DE by DP at constant S. Right? So the second derivative can be easily expressed in terms of these quantities. So ESS nothing but E squared E by DES squared, of course at fixed B, so which means we are considering E as a function of S and B and simply differentiating it twice with respect to S. That is the meaning of that. Similarly for the other quantities. Right. So now ESS is clearly dt by ds at fixed B. This is greater than 0, right? So from this I get t as a function of s and b, right? So since dt by ds is not equal to 0, it's greater than 0, but I don't require positivity, but all I require is to be not equal to 0 for me to consider the inverse function s as a function of e and t, right? Because the derivative is not, that's a condition specified by the implicit function theorem, it is a sufficient condition. So then I can, the inverse exists means the inverse derivative also exists. The derivative of the inverse function is simply the inverse of the original derivative. And this is of course equal to P divided by CV. So the condition that this is actually greater than 0 implies the positivity of the specific heat at constant volume, right? Specific heat at constant volume is positive. Let's now look at what the EBB greater than 0 means. EBB is the negative of, rather EB, this is minus dP by dV at constant S. If this is to be greater than 0, then clearly dP by dV at S is less than 0. Maybe we should, you can think about the arguments. I'm not yet sure if this is follows from, but certainly EBB not equal to 0 is a condition of invertibility for the Legendre transform h to exist. Whether we can conclude it's greater than 0, maybe we didn't go into it carefully enough, but I take that as given. You can think and convince yourself that. So this is equal to 0, less than 0. Now we defined a quantity called the isentropic compressibility. Right? So the isentropic compressibility is defined as minus 1 over p dv by dt at x. Since this is greater than 0, certainly it's not equal to 0, so I can easily form this derivative, right? So if dp by dt is then 1 over dv by dp, right? So this is less than 0, which means that the isentropic compressibility is greater than 0 as per the criteria of stability. So some of these points which we have already assumed, right? For example, we started out saying on physical considerations, experimental considerations, dp by dv is greater than 0. That's what is observed experimentally. But these now follow as conditions of stability. That's another point in favor of Gibbs's theory, that many of the experimentally observed features are. Excuse me, what is that conversation going on? Can you come forward? No, I don't want. I have been observing both of you for the past few classes. Please come here and sit. It's very distracting. Do you think this is a picnic or a class? Just come somewhere else. So this is the isentropic compressibility that is greater than 0. That's another one of the conditions. Now, to make sense of this quantity, what is to make further use of this inequality? Right? We will relate it to the second order derivatives of A with respect to B and T. Now we know that dA is minus. So this will lead to a. We look at the assignment problems. Problem number 4, for instance, it gives the relationship. You are asked to prove the relationship between the second derivatives of the Legendre transforms, right? So we will prove it for this specific case, and I leave it for you to prove the general relation. So I have this. Now from this again, dA by dt at B is minus S, and dA by dv at T is minus T. Now, if you look at this, let's look at what is dA by dt square, dA by dt square. dA by dt squared is at fixed V. This is minus ds by dt at B, which I know is minus Cv over D, which I have already shown that Cv is greater than 0. So minus Cv over T is actually less than 0. So I simply get this. We'll look at the significance of this later. But also importantly, since this is minus 1 over dt by ds at B, I can also write this as minus 1 over ESS. So we now get a relationship between the second order derivatives of A with respect to one of its natural variables with the second order derivative of epsilon with respect to its variable S. You can easily now look at the general expressions given and see if this arrives as a consequence. The general y as a function of x1 and x2, y is epsilon or the specific internal energy, S is x1 and b is x2. So t would be m1 and m2 would be minus p, right? So you can verify. Those are easy. We take up the general proof later, maybe in the next class. But for now, these are important relations. Now, if I want to see what is d squared a, now these nice expressions seem to come out for the pure second order derivatives. Not the mixed ones might be much more, might not have a simple form. Now let's look at what is d squared a by dv squared at t, right? And now this is minus dp by dv at constant temperature. So now I see, now I want to relate this, just as I related this to, as it is, I know what can you say about d squared a by dv squared yet, it will become clear when I relate it. So the two issues, even though look separate, the relationship between the Legendre transform second derivatives and the original second derivative, they are connected as we will see, right? So what I would point out is that now if I want to relate it, I see that ESS is dp by ds and EBB is dp by dv at s. Right? So if we want to relate it, I can clearly see a relationship between this and this, which we have already sort of derived when we look at the formula for the speed of sound, propagation of sound. We saw that the coefficient that came there was dp by dv at constant s, and we related it to dp by dv at constant t. In fact, we proved that is gamma times. But we are not going to look at it that way. What I am going to do is now look at this slightly differently. So I could see that dp, now if I want to relate the two, I have p as a function of b and t, which I can regard as coming from p as a function of b and s, and x expressed as a function of b and t. So I can now write dp by dv at t as dp by dv at s plus dp by ds at constant p times ds by dv at t. Now normally I would have replaced this with the using the Maxwell's relation in terms of the objective here is different. Actually, I would have been quite happy with this because this is directly obtainable from a pressure explicit equation of state. But here my purpose is different. I want to relate this coefficient, that is the second derivative, to the second derivative of epsilon with respect to s and p, right? So now what I want to do is, this is fine, this is as it is. This is in fact dp by dv at s is simply minus EBB. Now what is this? dp by ds at constant b. Looking at this, dp by ds minus c at constant dp by ds at constant b, so I can differentiate it. This would be what in terms of the second derivative of ESV, right? Minus ESV or EBS, both are same. So minus ESV. And now ds by dv, I can see that that is related to dp by ds, which is ESS. So I'm going to write it slightly differently. So I'm going to look at this as d equal to t of sp, leading to s equal to s of dv. And from this, I would easily show that ds by dv is negative from the implicit function theorem. The negative of dt by dv at x by dt by ds at b. We recall these. You can remember a couple of these formulas, and you will see that you can just sort of see where you need them and apply them appropriately. So this we have. So what is this now? This is minus dt by dv at x, right? D is this. dt by dv is EBS. Let me write it as EBS. This is minus EBS. It is equal to ESP. Divided by dt by ds at constant p is ESS. So my purpose here is different. So I'm doing all this, right? So I get minus EBS divided by ESS, and so now I'm getting dv by dv. So d squared a by dv squared, which I can write as ABB, is equal to negative of this, which is EBB minus, so this there's a plus here, so that will now become a minus, so ESB squared by, by ESS, which is equal to ESS EBB minus ESB squared divided by ESS. So clearly that is the coefficient that I have here, right? ESS EBB minus ESB squared is what I have is from the stability gradient greater than or equal to 0. Right now somehow I have to convince that it has to be actually greater than 0. ESS is greater than 0, EBB I somehow conclude that it's greater than 0. Now ESB, what is ESB? ESB is E by ds at t. Yeah, I think we have to conclude that this is greater than, both of these are greater than 0. So why is it that it cannot be 0? Somehow I need to show that. Okay, I'm not able to think further. But you have to show that if you can conclude that this is actually greater than 0, and then what does it, this I already know is greater than 0. So from this what I get is minus dt by dv at constant temperature is greater than 0 to dt by dv constant temperature is less than 0. Right? So I sort of remove the 0 here, which I will think about, and I think I'm just missing something. I'm not able to conclude how that, but it can be shown. It can be shown that that is also greater than 0. You can remove the equal to 0 sign. It becomes a strict inequality, and then so this is greater than 0. This is greater than 0. So we get this important. This would also mean that the isothermal compressibility is greater than 0. Okay. We get all these relations. The important is also there is a pattern in the way the second order derivatives are related of the Legendre transform. That is given in more detail in the assignment. Now we can look at, we have exhausted whatever we could get from A and E, right? So we can also write, I will just write down the rest of the relations which simply follow from. So effectively what we are getting here is also A TT is less than 0 and also A is actually greater than 0. Right? And similarly, we have here ESS as well as EBB. Both are actually greater than 0. Apart from what they imply for the various coefficients, right? So now if you look at the other functions h and g, I can easily show the following relations. HPP is simply minus 1 over EBB. That can be shown. It's almost analogous to this. ATE is minus 1 over ESS. The variable that is removed, and this is a new variable, and the second derivative of the Legendre transforms are related. Now, if you recall, H is something that is obtained by removing the volume and replacing it by the pressure. And so, of course, there's a minus there, but since you differentiate it twice, that minus will cancel and you still get minus 1 over EBB. So, this formula is very similar to this and can probably be written by inspection, right? But you can also prove it. And HSS is given by ESSEBB minus ESB squared by EBB. So the only difference from here is that instead of ESS, I'm having EBB. Right? So again, there is a certain pattern. You might want to look at the assignment sheet and infer how the pattern comes about. Now, what can be confirmed from this? What is HPP? Right? So I already know that EBB is greater than 0. Right? So this would have to be less than 0. HPP. Now, what about this? Both of these are greater than 0. This, of course, I have left somewhat unsettled. So HSS is also greater than 0. Now, what would this mean in terms of actual practically useful coefficients? Now, if you look at this, DH is PDS plus PDP. So, DH by dP is P. So HPP is simply dV by dP at S. That is turning out to be less than 0. So what it implies we already have, right? And that is the isentropic compressibility. I might have written here, right? So isentropic compressibility. So this would be, in terms of the coefficient, this would mean that this is actually greater than 0. Because both the isentropic and isotropic have a negative sign in their definition. That will cancel with this dV by dV. Minus 1 over V times dV by dV at S. So that will become positive. So we don't get anything new from this. Now what about HSS? That will show that the specific heat at constant pressure will be positive. As you can clearly see that HSS is T. So HSS is dP by ds at P. And I know that's greater than 0, so it doesn't vanish, so I can invert it and write it as 1 over ds by dt at P, which is equal to simply P over Cp. So if that is greater than 0, then I get that Cp is greater than 0. Having done all this, G is probably not going to give anything, but I can also write the general formula for G. I write it slightly differently, not in terms of the internal energy, but rather in terms of the two functions from which it may be appear to form directly, that is A and H. So it so happens that GPP is given by minus 1 over ABD. Again, similar. G is obtained from A by eliminating B and replacing it by B, so it has this nice relation. In the same way, GTT turns out to be minus 1 over HSS. Again, H is a function of S and P, and we have seen how from H we can get the G by H minus Ts, which means I am eliminating S and replacing it with P. So those second order derivatives also have that nice relation, just a negative of the inverse. You can see now a pattern. But you can also prove this. So what do we get from this? Well, I already know that ABB, what it is, right, is dB by dB at T. So all this is going to give. So clearly, ABB is greater than 0. So GPP is less than 0, and so is GPP. But they are probably not going to give anything. All this is going to give is that, Cp is greater than 0. This is going to give the isothermal compressibility is positive. So all the stability criteria is established as facts already known, namely the positivity of the specific heats and the compressibilities, right? But there's another feature to this. If you see here, what are all the coefficients, the second derivatives that are greater than 0? This is an interesting point made by many books. This is specific variable. So you see, this is, I'm talking about only the full second order, pure second order, not the mixed ones, right? So if you look at the pure second order derivatives, ESS, EBB, both are positive. Now if I go here, ABB is greater than 0. So when it comes to specific variables, the second order derivatives of any of the fundamental functions are greater than 0, but when it comes to intensive variables, they are less than 0. That's an interesting pattern. Again, you see here, if you are always worried about the sign, you just see what is the variable. Is it intensive or specific? Intensive less than 0, specific greater than 0. These are all only with respect to the natural variables, because I know I can also express T as a function of T and B or T and S or whatever. But those derivatives we are not worried about. Derivatives of the fundamental functions with respect to their natural variables, the second order derivatives follow a certain pattern. The derivatives are with respect to the intensive variables, they invariably turn out to be negative as required by stability. Here for G, both of them are intensive, so both the pure second order derivatives turn out to be negative. What they imply, of course, are finally, so this is regarded as expressing complexity of the fundamental functions with respect to the specific variables. Convexity always is associated with the positivity of the second order derivative. So we can regard it, this is not to be confused with the convexity of the fundamental surface that I pointed out. That's somewhat different, but this is similar. The derivative conditions are similar to the convexity conditions with respect to the specific variables, and concavity with respect to the intensive variables. Other than that, what I have is from the coefficients that we have already seen, all these coefficients are turned out to be positive as required by the stability criteria. Are there any questions? This is as much you need to know, but you should have some familiarity with dealing with second order derivatives also. That is a part that may not be required too much in this course, but since we have encountered it, so you should be familiar with how to handle relation between second order derivatives of various functions, right? So I have given some example here, and you can also take up the general principle that is given there. Maybe I will just point out how to do it generally so that you can get this. So only thing I have quite clear is how I concluded that this group of terms is actually greater than 0. So I think I will explain that next class, but some of you might have already figured out what is the logic. Clearly for ESS there is no problem. Even for EVB I think there was slight confusion. I sort of concluded then that it's greater than or equal to 0, and from the invertibility conditions for the Legendre transform it is greater than 0. That group of terms you can conclude that it is greater than 0. I don't quite see how the logic proceeds, but I will handle that later. But now you take a general case. Now I will define first I take just psi 1. I will demonstrate how to proceed, because here you have seen all the variables and the derivatives are physically variables. Here we look at it more from a mathematical point of view, how to relate the second order derivative. So psi 1 is actually y minus m1 x1. You can easily show d psi 1 is dy minus m1 dx1 minus x1. This is very important. So before we take the second derivative, we should know what the first derivatives are. Right? So, this is m1 dx1 plus m2 dx2 minus m1 dx1 minus x1 dm1. So I have cancelled this, so I get minus x1 dm1 plus m2 dx2. So from this I clearly can infer that d psi 1 by dm1. Now it's very important that you keep the variables explicit. Right? I know psi 1 is expressible as a function of natural variables are m1 and x2. So these derivatives are with respect to those variables. And d psi 1 by dx2 with m1 fixed is simply m2. So now let's take just these two examples and see how the pure second order derivatives are going to look up. You can also work on as an exercise the mixed second order derivatives and find out what kind of formula you're getting, but I'm not interested in that. So here is this. So now if I want to calculate d squared psi 1 by dm1 square, right? This is what I would look at. Right? So what is that? The d squared psi 1 by dm1 square, that is, you will now find that when you come to second order derivatives, all this manipulation with differentials will not help that much. Right? So you have to be very careful. Better always to deal with the derivatives rather than just look at. Here of course I have done it to get the formula quickly, that is fine, but this will find much more difficult to do when it comes to second order derivatives. The concept of differential is not very clear. Right? D squared, so I have to just differentiate. What this means is that I'm differentiating this again with respect to m1. Of course keeping x2 fixed, that is obvious. So I have to do the same thing here. So you have to now recognize, though x1 is an independent variable here, it is now going to be differentiated because this is a function now of m1 and x2. Right? So that's very important to keep in mind. So I have the m1 x2. Now another important point, because otherwise you can get confused with all these manipulations. What are we now going to want? What we want are the second derivatives of y to be related to this. Right? That's the objective. I can leave it as it is, right? But we want to relate it. So for that, it is important to know that dy by dx1 is m1, which is of course a function now of x1, x2, and dy by dx2, keeping x1 fixed as m2, which here is a function of x1 and x2. Right? So what would be d squared y by dx1 squared? It would be dm1 by dx1, keeping x2 fixed, and so on. Right? So now I have x1 as a function of m1 and x2. So clearly, right, if I want to look at this derivative, how could I relate this to these derivatives, dm1 by dx1 or dm1 by dx2? So we obviously have to regard this, where this is coming from, right? This is coming from m1 equal to some function of x1, x2. If I invert this, I will get x1 as a function of m1 and x2. Right. So clearly, this is one starting point. The derivatives of the function that we are interested in. First derivative, first you have to establish without doubt. Right? Then only we can take the second derivative. Now I look at the second derivative. The crucial point would be m1 as a function of m1 as x1 and x2 coming from here, and m2 as a function of x1 and x2. This is the basis, because the original starting point is y and its derivatives. M1 and m2 are defined directly with respect to y. So now what I have is, from the inverse function theorem, I clearly get it. Right? This is where the condition would come in, dm1 by dx1 not equal to 0. I'm not going to look at it, but I'm using that condition. Right? So if I now look at this, I can clearly write that dx1 by dm1, right, keeping x2 fixed, is 1 over dm1 by dx1 keeping x2 fixed. That is the inverse function theorem. That's what it says. So clearly then this is equal to minus 1 over dm1 by dx1 given x2 fixed. Now I'm back to m1 in terms of its natural variable, the first representation. So what is dm1 by dx1, but now keeping x2 fixed? What is that? If you look at this, d squared y by dx1 squared, that's exactly what I want. This is how this is of course keeping x2 fixed. So I've got what I wanted. I've expressed one of the pure second order derivatives in terms of the second order derivative of the original function, right, with respect to its variable. Now let us get to the second one, d squared psi 1 by dx2 squared. How to apply? That's what is going to give us a mixture of terms. This is fairly straightforward, but the same principle holds. So I just have to keep my eye on what are the variables and what I want to be transformed into. Right? So again, d squared psi, so d psi 1 by dx2 m1, because I want d squared psi 1 by dx2 squared. Right? So I'll take first the first derivative, that is m2. And of course this is expressed as a function of m1 and x2. That's obvious, right? So function of m1 x2. Now what is d squared psi 1 by dx2 squared m1 is equal to dm2 by dx2, right, at fixed m1. So now I am looking at m2 expressed as a function of x2 and m1. So I have this. Now what do I do with this? Right now again, the objective is to express m2 as a function of, m2 is naturally a function of x1 and x2. But what I want is m2 expressed as a function of m1 and x2. So I start from this m2 of x1 x2. To get to this, I need m2 as a function of m1 and x2. x2 is the same, but m1 is the new variable. So clearly I want x1 to be expressed as a function of, and this is why m1, and so there's two levels of transformation involved in this, and that's why formula also is a bit more complicated. So I have m2 expressed as a function of x1, in turn expressed as a function of m1 and x2. Right? I've already handled that there, that I know I can do it. That is coming from m1 expressed as a function of x1 and x2, but inversion x2. Now I will write dm2 by dx2 at fixed m1 from the chain rule now. This is probably the most difficult part. Is equal to dm2 by dx2, keeping m1 fixed. That is coming from this representation, right? So that is dm2 by dx1, right? Very important again, keeping x2 fixed. Very important for you to now keep track of the variables, and you will see why. Now I have dx1 by dx2, keeping m1 fixed. This is a puzzling derivative, because if you look at the original function, x1 and x2 are independent variables. So you might think that dx1 by dx2 is actually to be taken to be 0. This is what you might end up doing if you don't keep track of what you are differentiating with respect to what and keeping what fixed. So this is merely the variable x1 expressed as a function of m1 and x2. But keeping, then it becomes makes sense that I am differentiating with respect to x2, keeping m1 fixed. Right? In this representation, y as a function of x1 and x2, dx1 by dx2 will be 0. They are independent variables. Right? So that is what you have to keep in mind. So this is what it is. Plus I get another term. Right? That would be a dm2 by dx2 with x1 fixed. That will be the other term. That is not being transferred, so I'm just going to get that transformed. So I'm going to just get that term. Now what I have to do is, this is very clearly, what is this? dm2 by dx2 keeping x2 fixed. That is my original representation. So this is d squared y by dx1 dx2. That's very clear. Now this dm2 by dx2, what is that? D squared y by dx2 squared. So I have got that also. So all I am left with is expressing this. Now this, if you see again, x1 expressed as a function of m1 and x2. Again, this is coming from m1 expressed as a function of x1 and x2. 2, x1 expressed as a function of m1 and x2. And probably already dealt with there. But there I got the one of the derivatives. Here I need the other derivative. Right? So from here itself, this is one. Now the second one, dx1 by dx2, giving m1 fixed. I didn't write it because I didn't need it then. But I can easily write this as minus dm1 by dx1 x2 dm1 by dx2 x1. That's again coming from the inverse function theorem. So all I have to do is to substitute it there, and so clearly that derivative dx1 by dx2 giving m1 fixed is minus dm1 by dx2 giving x1 fixed. That is d squared y by dx1 dx2 or dx2 dx1. squared. So dm1 by dx1, that is d squared y by dx1 squared dx2 fixed. Now we put all of them together and verify the formula given here. The first, that is the fourth problem A, the second of the formula, d squared psi 1 by dx2 squared. If you are able to get that, right, I might have made some mistake in sign. This is the procedure you have to keep in mind. This is not very easy to do, but you have to be really careful, because I've seen books do all kinds of manipulation. I've seen at least 2 glaring errors in second order derivatives of Legendre transform in 2 very famous books. I won't mention those books, right? So it's not something that is easy. It might look easy and tempting to simplify some of these, but you have to be very careful how the variables are going to be transferred. The good thing is, for most of the course, we don't really need this kind of a complicated, calculus. Mostly dealing with first order derivatives and their integrals, right? So anyway, we'll take up some of the other assignment problems on the class on Monday.